So remember, before this we have discussed on the forces that is applied to M1, and we have to, if you could see here, the forces applied Ft, and then we have to imagine that M1 is moving to the right while we held the M2 still, and then we see those forces. And so meaning that we have to list down the forces that are due to the motion of M1, which relative to X1. And then there are also the forces that are due to the forces on M1, but due to the motion of M2, meaning that imagine M2 is moving to the right while M1 is held still. So there are forces, those forces are relative to the displacement of X2. So when we sum all those forces on M1, we will have this resultant forces, which is the superposition of displacement of X1 and X2. So if you could see here, the yellow one is due to the displacement of X1, and the blue highlighter is resultant of the displacement of X2. So when we want to write the equation, first we look at the mass one, M1, and you could see here the first one is because of the mass itself, which move with an acceleration m1 s squared, and then you have this Fv1, which is the friction on the surface, and then Fv3, which is due to the damper, and then don't left out this S, and then you've got the spring due to K1 and K2. So all of these forces are relative to the displacement of X1 S, and then U minus with the displacement relative to X2. So you have this Fv3, which is the resultant of the damper, okay, and then you have also K2 of a spring. So these two are result of the forces relative to X2, and then you equal to Ft, which is F as the Laplace transform of the Ft. So these equations are the result of the summation, the force summation or impedances that is applied to M1, and then we do a similar fashion to M2, okay? So you have to list down all the forces here. So you could see K2 and K3 is the spring, which is due to the spring relative to X2, and then you can see here there's friction on the surface Fv3, and then there's also the damper Fv3, okay, and then the acceleration of M2, and then this one is relative to X2 displacement. But you have to imagine that again, if you hold still M2 and you move, imagine that M1 is moving to the right, you have this another forces, impedances applied to M2. So there's Fv3, the damper relative to X1, and then there's K2, the spring relative to X1. So you list down, make the second equation, list down the second equation of M2. So now if you could see here, we're looking at M2. So we want to list down all the equations, all the forces in the equation, second equation. So that's the one that is relative to the displacement of X1s is only the damper Fv3 and K2. So always put negative here because we're looking at M2. And then once we imagine that M2 is moving to the right, then we imagine that M1 is moving due to the relative to the x1 displacement. And then we look at the relative to x2 displacement. So there's mass m2, and then there's a damper as well as the friction on the surface, and then there's spring k2 and k3, and then all of these are relative to the displacement of x2, and then equal to 0 because there's no input at m2, at the object m2. But for the first equation, there is input force at m1. So if you see there's two objects, meaning that there's 2 degrees of freedom, and you will get two equations relative to m1 and m2. So from there you can solve it with Cramer rule equation to get that transfer function of it can be x2 over fs or x1 over fs. So it depends on the question. So there you are. This is how you come up with the equation modeling.